Hi, hello. So, welcome to this session of 174.1. This is on the topic of temperature sensing itself. So, this is a bit of a new one for this course. So, please bear with us while we set things up. So, I hope the slides are kind of okay. So, there's my pointer. Right now, we're going to split the topic into two. Before we go into temperature sensing, I just want to talk about the platform that we'll be using, which is the Arduino board itself. So the Arduino board didn't come out of nowhere. It came from this desire by hobbyists to create their own circuitry, their own machinery, in a sense. However, that came with a lot of effort, such that this kind of hobbyist pursuit is kind of locked in to STEM creators, STEM innovators, and although technically this kind of technology can revolutionize other non-STEM fields, it takes a very steep learning curve in order to get in. So there were a few people, some students and a panel of professors. They decided, oh, okay, what if we created an open source platform that is easy enough such that even people from outside of STEM can effectively learn their way into using electronics. So that is when they started to develop this open source platform. It's not Arduino yet, it's under a particular name. Um, However, one of the professors, or one or two of them, created a fork out of that project, and that project was named Arduino, or rather the company that produces the boards. They're called Arduino. And eventually, the Arduino board became one of the most prevalent open source microcontroller platforms all over the world. Um, so even though Arduino is kind of being produced by one company, technically it is still open source. You can create forks, so to speak, of Arduino. So if you're knowledgeable in the realm of PICs itself, you can create a custom kind of Arduino board depending on your use. However, for the Philippines, you will typically see two kinds of boards that are available. The first one is the Uno R3, or at least the Uno family of boards. This is, as I mentioned, this is the very first series of Arduino microcontroller boards. And I believe there is already R4 that's available at the time of recording. And the second one is the Arduino Nano. Now, just to make it clear, there are two terms that float around with respect to the Arduino board. So we call these as microcontrollers. When we say microcontroller, this is specifically referring to a platform, essentially a CPU that has all of its peripherals, all that it will ever need integrated into a single board. Basically, it's like a tiny, tiny computer, and the only thing that it needs are sensors in order to gather data and displays or connections to output displays to show you the results. So the thing with the microcontroller is that it's a very compact and very fast um, board. However, it's quite limited in the scale of computations that it can take. So this is in comparison to what we have in our laptops and our desktops. The microprocessor is actually just a CPU um, with some attachments, but it has to be supported by external peripherals. Now, the advantage here is that due to the architecture of the microprocessor, it although it's not as fast as a controller, it is kind of beefier. It can be specialized, and it can be made to do tasks that are kind of more intensive compared to the microcontroller. So the advantage of the Arduino is that it's quite portable and it can do um, smaller scale calculations very fast. Now let's look at the Arduino board, specifically its inputs and output pins. So this is what we call the pinout diagram. It helps people orient themselves. Okay, so what is the address of this particular pin? This one we will not dwell into too much because we won't be exploring the basics of Arduino. Usually we'd rather have it prepared for you, partially at least. But we'll just look at the parts. So first and foremost, we have this standalone power jack. So this is for the round socket. If you do have it, you can place it. You can use that to power the Arduino. You also have the USB port. This port can transmit data and power. So if you have your device hooked up to your Arduino, you do not necessarily have to provide separate power. At least not quite yet. There's also the reset button, but I'm not sure if it's relevant for some applications, but we don't typically use it anymore, at least for our case. The next is when we turn our attention to the left side, to the left part of the board, we have two main sections. We have the supply pins. So the supply pins take care of the supply of the sensors, the relays, the displays. So that this includes the VCC. So the VCC here would have the 3.3 volts out and the 5 volts out pins here. So those pins are what you will use to power those sensors and displays. You also have two ground ports and you have a voltage in port. So this is in case you want to power Arduino um, in a way that doesn't involve the power jack and the USB port. Now, further down, we have our analog to digital conversion pins. So this is where you collect, or rather connect sensors or relays that um, send back um, data that is in a spectrum. So, or a scale rather. So one example of that is voltage level. So voltage can be 0 to 6 volts. So that is kind of on a spectrum, and that spectrum will be divided up and converted into a digital signal. Now, on the right of the board, we have in particular two inter-integrated circuit pins or I2Cs. The unique part about this is that this is where the Arduino will send data to, like for example, an LCD display that is also an I2C. These are the two data ports that you will need to connect to the LCD display in order to have it display numbers, letters, and whatnot. Now, further down, the majority of the right side, quote unquote, right side of the board is occupied by digital pins. Now, the digital pins, they can be inputs or outputs, but the rule is that they can only send and receive zeros and ones, binary signals. Now, to go over it again, so the supply pins, they typically take care of the power of the peripherals, sometimes the displays as well. You cannot use the supply pins to power motors. Maybe you have this bright idea to hook up a motor directly to the Arduino board. The Arduino board cannot supply enough voltage to move even a 3-volt motor. You can try, but it will be quite slow and it cannot really receive a lot of load. Much more a servo motor or a very big motor, a very big DC motor rather. You need something else, but that is out of the scope of our lecture. Now, there's also the analog pins. Now, to clarify, Arduino converts the entire spectrum of outputs of your analog sensors into a range of values from 0 to 1023. So all in all, you have 1024 bits, again ranging from 0 to 1023. And what are the sensors that you can connect to these pins? So from left to right, you can have your soil moisture sensor here. It's kind of like a tuning fork. You can have your temperature sensors, your current sensors, voltage sensors, and relative humidity sensors. So basically anything that sends back data that is usually on a scale or on a spectrum. Now, again, on the right side, you have digital pins. Again, these can serve as inputs from sensors. What kinds of sensors? I believe you can use that for speed sensors. So basically, you just receive a whole bunch of zeros and ones, and the board can interpret that as some kind of RPM or some kind of frequency. Now you can also use these to send out control signals to motors, pumps, and other kinds of motile components. Unfortunately, again, these are just control pulses. They cannot switch on or off, or rather, they cannot control fully the motor on its own. Like you need something else, but that is again out of the scope of our lecture. Now, coupled with the Arduino board itself, you also have your integrated development environment or the IDE. So usually when you buy or use an Arduino platform, you want to get an Arduino IDE. This is kind of like a script editor that is very beefy. Like it's essentially a compiler, a code checker, everything almost. Like it's kind of like a very user friendly script editor. And again, if you have some expertise, or rather even not expertise, if you have experience with C++, or Python code, you can handle typing basic code on the Arduino IDE. Now, if you do not want to create your own script, there are actually plenty of scripts available online. People are committed to the open source bit. So if in case you're using a any kind of sensor that we might not cover in this course, there will surely be someone who is kind enough, generous enough to provide their own code that is probably user base verified, user base tested, and it will work. Now, also, if ever you do not have an Arduino board, which is probably most of you, but you still want to explore the possible circuitry that you can develop using the Arduino board, there is a blessing in the form of Autodesk Tinkercad. So Tinkercad is actually free, but since we all have Autodesk accounts in UPLB, you can avail of the Tinkercad. Maybe there's some extra service there, I'm not sure, but yeah, you can actually simulate the Arduino board along with several other electronic components online or on the cloud. And the neat thing about this is that there is also a simulation up to the Arduino IDE level. So like you can actually code and have Tinkercad simulate that code for you. So that's quite interesting. Now we go to the temperature sensors themselves. So temperature sensors aren't exactly new to us in mechanical engineering, especially if you've already gone through NSci 14. So the most iconic temperature sensor that we have is the liquid thermometer. So the liquid thermometer uses fluid density change in order to display any changes in the temperature. So the one pictured here is an alcohol thermometer. We do have mercury thermometers, but they're quite dangerous. Yeah, they're quite dangerous. The other more common temperature sensor is the bimetallic strip. So basically, this is a strip of two dissimilar metals. When you heat up the strip, those two metals expand at different rates. causing the expansion or the contraction of your coil. Now, the bimetallic strip has been used in, like for example, temperature gauges for a while. They're also used for thermostats, at least ye olde thermostats back in the day. Another common way of sensing temperatures is by using the black body radiation phenomena. So this is how temperature guns work, essentially. So these are three very familiar temperature sensing devices. Now, of course, in the age of electronics, we do have phenomena or other materials that have temperature dependent characteristics. So the first of these is the variable resistance. Now, there are certain materials that do have a change in resistance depending on the temperature. And what we do is we pass some electric current through that material and we record the change in the output voltage, and then we correlate that with the resistance, and then we correlate that to the temperature. So the cheapest and simplest out of all of these electronic sensors is the thermistor. Now take note, the thermistor that you see here is zoomed in, like it's very zoomed in. Thermistors, especially the generic ones, are very small. You can easily lose one if you're not careful. And they typically use semiconductors as the thermistor component, the variable resistance component, I mean. Now, a heavy step in advance to the thermistor is what we call the resistance temperature detector, or the RTD. Now, the RTD is quite advanced. It has a metal wire and it's wrapped in ceramic. So you can imagine the fragility of the sensor. And of course, when it comes to fragile things, normally you build these out of a reason. Like you don't just create a very expensive ceramic lined metal tube just to be fancy. So we'll discuss the intricacies of that later. Now, aside from variable resistance, there are also phenomena that are linked to varying electrical potential. Now, this phenomenon is called the Seebeck effect. So, when there is a differential, or rather, when there's a temperature gradient along a strip of metal or a piece of metal, there will be an electromotive force or a generated voltage within that material, and we can actually measure that and use that in order to estimate the temperature. And that is how thermocouples work. So those are thermocouples. They are different from thermistors. What other differences do they have? We'll discuss later as well. And the last one that I want to focus on, I think this is a new discovery for me, but I think it's existed for a while. These are the proportional to absolute temperature sensors, or the PAT, or the PTAT sensors. I am actually not versed in reading schematic diagrams for electronic circuits. However, what we do know about them is that these sensors are factory calibrated. They do not need to be retuned after you procure them, and they can actually report immediately the degree centigrade or the degree Fahrenheit of its surroundings. So this is unique actually in comparison to the others. We'll see why later. First, let's focus on the thermistors, or rather the variable resistance sensors. Um, Again, these sensors have varying resistances with respect to temperature, and there are actually three kinds of them. Let's focus on the RTD first. So, what you notice with the RTD, the green graph here, is that its slope is kind of steady in a particular range. So, it's sort of linear at a certain point. And this is actually something that we desire out of the RTD. It has a very stable temperature gradient, and it is actually quite precise. It is also usable in a wide temperature range in comparison, at least to the other variable resistance sensors. However, again, this is metal wrapped with ceramic, so it's very expensive, and also um, it is quite slow to respond. So even if the temperature in the room change suddenly from very humid to very cold and dry immediately, the RTD will need some time to catch up, at least, to the temperature changes. Now, the opposite of this is the NTC. The NTC is a thermistor. It means negative temperature coefficient thermistor. So this is the other end. So if the RTD is the most expensive sensor in the slide, the NTC is the cheapest one on the slide. And as you can see in the graph, the NTC's resistance degrades with temperature. Now, the good thing about this is that NTCs are quite cheap, as in they're dirt cheap. Cheap, like literally, you can buy a bag of them for no for chump change essentially, and they're actually quick to respond. Like, they're very responsive. So if you have a very dynamic experimental setup, you might want to consider thermistors in there. However, the problem with the NTCs is that they have a very tight range, especially the generic ones. If you buy an NTC thermistor off the online market, the typical range would be -30 to 130. Now that might be good for our vac application. So like if it's just for climate control, yeah, NTCs are good. However, if you're monitoring combustion or fluid heating, something like that, I don't think NTCs will be for you. So yeah, they're very cheap, but they do have a narrow range in comparison to the RTD. Now, the last one, the PTC, of course, this is the positive temperature coefficient. The thing with the PTCs is that they're kind of overshadowed by the NTCs. Rather than being used as sensors that report data, they are used to detect very sudden changes in temperatures. As you will see here in the graph, at a certain point, because of the exponential relationship of the resistance to the temperature, there will be a point wherein it just suddenly goes up. And you can use that to your advantage, especially in circuit protection. So you will see PTCs as some kind of part of a resettable fuse. Again, so there are fuses that are non-sacrificial that you can actually reuse. So PTCs are one of the components to make that possible. So yeah, we have our TDs that are very expensive, very precise, but very slow. And then we have NTCs, which are dirt cheap, very quick to respond, but have a narrow range. Now for the PTC, if you are going to use this as a thermistor, the range is even narrower. If your NTCs have a range typically of -30 to 130-ish, depends on your supplier. The PTCs have a 60 to 100 plus degrees centigrade range. So that's higher than room temp, and that's quite a narrow range. So you see why they don't get used often as sensors. All right. Just checking some things. All right. So yeah, those are thermistor behaviors. Um, the experiment that will follow this would focus on the NTC thermistor behavior, but I can see that perhaps down the line we could look at the behavior of other kinds of temperature sensors. So, forgive me for the, just in case if you're watching this from the future and this slide is quite antiquated, I am so sorry. So yeah, let's go on ahead. So let's look at the thermistor models. So this in particular is focused on the NTCs. So for the NTCs, we are expecting a exponential decay of resistance with respect to temperature. And there are three models that we can use. The first one is, of course, the dumbest one, which is the first order approximation. Of course, you're gonna approximate an exponential curve using a linear model. Where could we go wrong? Of course, it's too narrow. We can't use this. The other end is the most precise one, which is the Steinhardt-Hart equation. Yes, it's a Steinhardt-Hart equation. This one is the most accurate one. However, you do need three three temperature points here in order to confirm the coefficients. Now we can actually take this on. However, yeah, maybe in the future we can look at how to calculate the coefficients A, B, and C here. However, we'll leave that for future semesters. Now, the one that we would most likely encounter is the beta formula, or the beta model. So this one is just a straight up exponential decay equation or an exponential growth equation if you are using a PTC. So the beta formula is just as shown. So this resistance, which is a function of temperature, so you have this particular quantity, which is R, which is the resistance at the reference temperature. So this R naught. So R naught here should be advertised. So when you're buying NTC thermistors, it will usually come with a label. So like for example, if you buy MF52 thermistors, you might see 10,000 ohms. Now that 10,000 ohms is the resistance of that thermistor at 25 degrees Celsius. Normally, it's 25 degrees Celsius. I think they would mention otherwise if that's not the case. So T naught here is 25 degrees. Beta here is dependent on the material, and that material can introduce a lot of variability to the curve, the beta formula here. So normally they do supply an estimated value for beta. So like for example, if you have a thermistor, maybe its beta is around 3435 or something close to 4000. Normally for generic thermistors, you would see around 3000 to 4000 values of beta. And you will use this in order to predict the temperature of the environment or whatever it is that the thermistor is touching. So it's kind of a roundabout method. So normally you can't measure resistance off the bat. You have to measure something else. And normally you would take note of voltage differences, potential differences. So again, if you have a potential difference, you can calculate the resistance just by applying a particular kind of circuit. So from voltage, you measure the resistance, and then from the resistance, you can calculate the temperature. So that is it for thermistors. Now let's look at the thermocouples themselves. So if thermistors are so dirt cheap, why do we see thermocouples a lot in engineering? So there is actually a good answer for that. So the thermocouples, they have kind of a very low accuracy reputation. So they're not the best at readings. However, they are useful for a very, very wide temperature range. So just to illustrate how wide that range is, here is a graph. Here is a graph of different thermocouple materials, and look at that x-axis. So you have thermocouples that are functional from 0 to 1500 degrees Celsius. So this is combustor, like gas combustion chamber levels of temperatures, and they are functional. At least some of them, they look functional at that level, but they're about to die. So yeah, these are very versatile temperature sensors. In fact, the most common one that you would see, and the ones that you do see all around SEAT probably, is the K-type thermocouple. Now, the K-type is not specifically this blue-lined wire with yellow sockets. There are different quote-unquote formats or forms of type K But yes, type K will be the one that you would usually see. Now, type K, I think it depends on the manufacturer. Sometimes they would say that you should only use this for up to 180 degrees Celsius. But as you can see here, we have a graph that claims that if you make type K right, you could make it last until almost 1500 degrees Celsius. So I'm not privy into what kind of technology or manufacturing that you need, but normally those kinds of thermocouples, they're good for around 800 180 degrees Celsius unless otherwise mentioned. So that's the K type. And normally for the thermocouples, you do need a logger or a display. So when you buy a thermocouple, you also have to buy a display. And that display has to be compatible with the thermocouple ports. So you gotta watch out. If you wanna buy thermocouples, you should either bring your data logger or you should buy a data logger that is compatible with your thermocouple. Now, another thermocouple that I want to talk about is the Type T. Type T here is this little guy here. The good thing about Type T is that it's quite linear. Like, it's surprisingly stable as a thermocouple. Now, the stability here introduced here makes it attractive for low temperature applications, especially cryogenics. Now, if you're curious, okay, what are the types indicating? The types in the graph indicate a combination of metals. Now, K-type thermocouples, they use chromel and alumel. So, chromel is 90% nickel, 10% chromium, while alumel is 95% nickel and some other metals. So, of course, aluminum is included because there's alum in the name. Now, T-type here is mostly copper. So, it's copper plus a copper alloy. That's constantan. Constantan is 55% copper and 45% nickel. Now, in order to compare all of these sensors, these are what we have. So we have four kinds of sensors. I'm so sorry we didn't focus on the IC sensor or the PTAT sensor. This is kind of a weak spot for me, but yeah. Here is Texas Instruments claimed general comparison table for the four kinds of sensors. So what you see here with the thermistor, that it's really in a special spot. Like it's really dependent on the material type. Because the thing with thermistors is that because it's kind of dirt cheap, you kind of have to look at the actual experimental performance. You have to calibrate the thermistor first before you give any comments. So yeah, because it's dirt cheap, the quality, the kinds of materials, the properties could change from unit to unit. But yeah, now the consistent thing about this is that the RTD is typically the best when it comes to accuracy. Like if you want precision measurements, you go for the RTD. Now, if you want ease of use, the next best thing is the IC sensor. The IC sensor or the LM35, I think that yeah, it's the LM35 sensor that we showed in the previous slide. The simplicity actually comes from the fact that all of the calculations to convert the absolute temperature to centigrade is already baked into the sensor. So like if you plug this into an Arduino circuit, the output pin will produce signals that you can easily convert into centigrade. Or maybe your sensor is calibrated to Fahrenheit. So you can use this and then have very little amount of support code in it. So this is quite simple. Like you just have to find okay, so which pin do I insert it into or connect it into, and then you're basically done. You don't need to calibrate the IC sensor, and that is the neat thing about it. The weakness, if I may comment on the IC sensor, is that this IC sensor is quite big. Well, it's small, but it's big in comparison to the thermistors. the thing with thermistors is that you might be able to put them in places that the other sensors might not be able to reach for a good amount of accuracy, of course. Now, again, this is the thermistor's advantage really depends on what material they used. So, if it's just a generic type, you will just get this generic range for the thermistor. But I believe that there are materials for the thermistors that can exceed this. Like, I've seen claims of thermistors reaching 300 degrees Celsius. So, I think, yeah, you just have to buy higher end thermistors for that. What you notice for the thermocouples is that they're really only good when it comes to the temperature range. So you can see here that they're not really beatable in with this respect. So if you don't know what you're measuring, you can just use thermocouples. Like, okay, I just want to tap my sensor on a random surfaces. I don't know if it's cold or hot. So yeah, you can use thermocouples if you're ready to use it for differing temperatures or differing ends of your plants. Unfortunately, it's not really the best in other categories, and it's kind of the worst in circuitry. I believe you need some here's a particular support peripherals in order to convert the thermocouple signal to something useful. I believe you need an amplifier for this. I do see that they sell amplifier peripherals or amplifier terminals in order to connect this to the Arduino. But yeah, it's kind of complex. For the RTDs, I believe the complexity lies with interpreting, understanding the circuitry and understanding what each wire usually, yeah, it could be 4 pin 3 pin sensors. I believe you just have to understand what all of the pins are doing. For the thermistor, it's just 2 pins usually, so it's quite kind of easy. For the IC sensor, okay, so one of them's ground, one of them's the power supply, and then the other one's the output that gives me the data, and that's it. So yeah, those are the various temperature sensors that you may encounter at this point. It depends on your eventual workplace if you're going to encounter any of them, or maybe you'll handle more advanced kinds of sensors. But that's basically it for this part. So, for the experiment, please await the activity guide and further instructions. Okay, thank you so much.